Okay. How about now? I think now. Okay. Okay, sorry, apologies for the Zoom. I sure haven't given away the punchline yet. So the two-point function has served as the main object of interest in traditional application of cosmological parameter inference up to this day, and has also seen tremendous progress towards efforts to model its dependence, its cosmological dependence, both analytical, using state-of-the-art perturbation theory approaches, but also computational using simulation, state-of-the-art. And this is great. However, we know that this is insufficient. It is insufficient because it fails to capture because it fails to capture the non-Gaussian amount of information that is involved in the cosmic density field. Or to put it differently, if the cosmic density field followed a Gaussian probability distribution, just like it was almost the case in the early universe, aside from primordial Gaussianity, all of the information would be encoded in the two-point function, all higher order correlations would vanish, and that would be the end. However, unfortunately, we know that this is not the case because of the action of the nonlinear process of gravitational instability, which is responsible for the formation of structure in the universe at late times, but this is also responsible for the emergence of non-Gaussian. And as a result, the informational content that the Parse spectrum encodes is insufficient, and which forces us, if we want to tackle these questions, to do something better. And perhaps the next step, the next logical step, if so to say, in order to overcome this difficulty, is always to extend our evaluations and include higher orders in the correlation function. Traditionally, we can evaluate the three-point correlation function, the four-point function, and so on, the endpoint function, which is indeed another subfield of cosmology that has seen a lot of progress in the past decade or so. Again, both using analytical approaches and simulations in light of this demand in the application of cosmology, but which unfortunately also quickly becomes intractable because of the fact that both literally the computational cost of evaluating higher function becomes very expensive, and also literally the dimensionality of the data vector itself also very quickly blows up. And so there's even an argument to be made actually that in the deep nonlinear scene, even if one knows all of the moments, maybe this still doesn't capture all of the information that's available. It's an open question. Now, in light of this difficulty in there, another parallel subfield of cosmology is centered on identifying some alternative summary statistics that essentially try to provide us with a shortcut towards accessing this higher information without having to evaluate all this, expensive hierarchy of correlation in the moments. And this is a very long list here. It's not by no means exhaustive, but it consists of some nonlinear transformation, for example, that try to pull some of this higher order information back to the two-point function. It consists of proxy estimators, environmental dependent statistics, voids, pick your favorite one, also pick your potential lenses. There's a long list of many others. Here I just showed an instance of the marked correlation function. You'll see later on what it is, because it's something I've worked on in the past in the context of testing gravity. And this is all great again. This is a very active field. But however, I think most of us, or if not all of us, agree that the extent to which this type of alternative techniques can give us again access to all the information that's available is still an open question. Now, on the other end of this, but in connection to this discussion, in the last decade or so, undoubtedly, artificial intelligence has quickly emerged with machine learning counterparts as a new, very ambitious tool that promises to potentially capture all of the information that can be encoded in a target, in a cluster physical field, or in a physical field, no matter how complicated. And indeed, you've all seen it, it has demonstrated tremendous progress and tremendous promise in the context of simulation-based approaches and applications, maybe even some preliminary applications to the data. But in general, it's plagued by a lot of issues related to, for example, interpretability. A neural net can be considered as a giant black box that requires a ton of training and can overfit, and it's hard to interpret what's going on. So even though it's obviously a tremendous tool, I think again, the extent to which this power can actually be harnessed in the real world using actual astronomy, or in our case, cosmology data, is still an open question. Now, the estimator that I'm going to be discussing today is one in connection with both of these fronts, let's say, of viewing this discussion is one that promises to essentially serve as a middle ground between these two, that tries to avoid some of the many shortcomings while retaining some of their main advantages. And this is called the wavelet scattering transform, which was proposed for the first time by mathematicians, by Stefan Malin and company, in the context first of signal processing and computer vision, but has been slowly making its way into the physical side. So, in case you haven't heard about this before, what is the wavelet scattering? Let's define. So, given an input field, which can be any physical field, in our case, as I'm going to talk about cosmology, this would be like the cosmic galaxy field. As you can see here, starting with such an input field, we start by performing a convolution, this star operating phase convolution of this field with a family of localized wavelets. And this family of wavelets, I will define exactly shortly in the next slide or two. But they can be viewed essentially, we start with a mother wavelet that spans a given physical scale and orientation, fundamental one for our system. And then by performing a series of dilations to the scale and a series of rotations, we can generate a group, a family of wavelets, which essentially can be viewed as a basis that captures the scales of interest in our system. And you will see how this can happen. Then after performing this convolution with each one of these wavelets, we take the modulus of the resulting fields, and then finally average over all its pixels. And this procedure here, which can be nicely illustrated on this figure on the right, you see that in this case, we start with an input 3D field, the cube, and you can see how performing the convolution with the various members of this family of wavelets generates many different versions of this original field for its scale, which then, after taking the modulus and average, give us a collection of numbers, and we call them W-based coefficients, at each given order. And more importantly, you can see that the successive subsequent repetition of this procedure gives us this tree-like architecture, like this cascade, that we call a scattering network. And at each layer of which, again, we end up with a collection of these coefficients. And you might be like, okay, this is fine, but why would this? What's the point? Or as a physicist, I would also ask, what is the physical meaning of this? So it turns out, let's look at this. First of all, a zeroth order. This is just not particularly informative. This is just the mean value of a field. But things get progressively more and more interesting as we increase the order of evaluation. So you see that at first order, when we convolve a field with a wavelet, the spans scale and orientation, essentially, this convolution, this procedure, will extract a number that characterizes the strength of clustering in this field around this given scale and orientation. In fact, you can see, if you remember, that if we replace this general wavelet just by a plain wave for reverbation, and if we raise this module to the power of 2, we literally end up with the power spectrum version of this. So you see that things start to get interesting because this can be essentially connected to something that can characterize the clustering of an input field. And things get more interesting if we do this once, if we keep repeating this. Because at second order, and according to the reasoning I laid out above, you see that when I extract such a coefficient, essentially I can characterize the strength of clustering of a cluster field, which is information related to essentially the correlation function of order 2 to the power of 2, so 4-point-like. So you see that the moment I did this twice, I'm able to access non-linear information beyond the power spectrum, which is of interest. So it turns out that this collection of numbers up to a given order can act as a basis that can characterize the cluster information in the field, just like in cosmology or in general. So in astronomy, we work with a familiar basis that consists of the 2-point function, the 3-point function, the 4-point function, and so on and so on. And it turns out, and many of these things mathematicians have proven, that this basis retains all of the familiar nice properties of the familiar power spectrum, such as, for example, it's stable against deformations, it can be isotropic and homogeneous and all the good stuff, all these nice symmetries of the field. But it also retains some information, or it retains some properties that are not captured by the standard power spectrum. For example, it's more compact. As you will see, the number of the coefficients we generate doesn't blow up as quickly as with an endpoint function. Also, you see, it's an important property that even though we talk about a higher order statistic, the input field, it always enters this operation in a linear fashion. This modulus there is always just power 1. or slightly away from 1, as opposed to an endpoint function where we raise the field to the power of n, which can amplify the noise in the field, make us more susceptible to outliers, numerical instabilities, and stuff like that. So, but perhaps the more important, like the more notable property of this, is that, as you can, maybe those of you familiar with machine learning might have already realized, this can be viewed as a shallow neural net, just a couple of layers, but with fixed kernels, which are these wavelets. Because remember, like fundamentally, if I want to be like very rough in my description, a CNN or a neural net essentially subjects the field to a series of convolutions, some kernels, and the non-linearity. And then some pooling, some average procedure. So you see here, it's a similar thing, but where the kernels are these wavelets, which are predetermined. So you can be viewed as a more interpretable middle ground of a neural net. In case where we want to do better than the standard point function, but we want something that's more interpretable. That's why I said a middle ground, which is something that's also very attractive in physical applications. And this type of technique has been proposed first to just shed light into the behavior of neural nets. But then it started to make its way, as I said, into the physical sciences, as people realized that it can also be a powerful tool for quantifying additional information and for parameter inference. And indeed, in 2020, there was the first application of this estimator in the context of simulations using weak lengths. I will talk about galaxy clustering, but another probe is weak gravitational density, shear maps in particular. So so here in this work by Sikao Cheng, Chris Menard, and people and Johns Hopkins collaborators, they took some simulated weak lengths and shear maps, and they performed the forecast. So in the center, you see this gray contour is the forecast of the errors one could obtain on two cosmological parameters, sigma 8 and omega matter, fundamental parameters we can determine using weak lengths. And then on the right, you see the equivalent contour one can get if we apply like a state-of-the-art, as they called it at the time, CNN. And then on the left, you see in the red contour what they got using this wavelet scattering transform coefficients. And I will show the configuration exactly shortly. So as you can see, not only did it better on power spectrum, but it did on par essentially with the state-of-the-art CNN. So it showed the ability to be very, very good for obtaining adequate constraint parameters. So, and you can see a nice plot that they made, which I've been meaning of making a similar one with my data, but I haven't done yet, where you see that we have three synthetic weak lengths in maps. The bottom one in the center is a Gaussian field. And then we increase the degree of Gaussianity. And you see on the left, they are chosen such that they have an almost indistinguishable power spectrum within the error bars. But you see on the right that by convolving with a particular chosen basis of these wavelets, we can expose distinctly different features in these three maps, which essentially means that a more sensitive estimator can allow us to discriminate between them, which essentially ideally would translate into our ability to use it to get strong constraints on parameters, on cosmological parameters. So this was all exciting, and exciting to me because I'm someone that has been thinking about these things also, but usually mostly in 3 dimensions. These both go together, but I will talk about 3D galaxy clustering in this talk. So I promise to just briefly, without getting into too many details, show you the wavelet I'm using. So the particular wavelet basis that we're going to use for this application is a 3D one, where it's called a solid harmonic, where you see that we have our familiar Laplacian spherical harmonics multiplied by a Gaussian that essentially multiplied actually by a radial polynomial, the solid harmonic, and then multiplied by Gaussian, which localizes essentially the support on a given scale. This is the mother wavelet in this case. It was first developed actually for applications of molecular chemistry, but in 3D, so it was already implemented, and we also chose to work with this. Actually, there's a public Python package if you want to play around with this kind of stuff, which is called Kimatio. When I give this talk abroad, I usually like to point out how Kimatio is wavelet, and I'm very happy about it. Perhaps it's not very surprising to see this here, but nevertheless, this is a name I strongly endorse. And this type of wavelet then, of course, captures a given scalar orientation and then can be dilated or through the rotations, through essentially the harmonic orientations, we're able to capture the angular information. There's many other bases actually more recent ongoing work. We are now working to develop better bases suitably tailored for cosmology, but the results I'm going to show here use this one. So, and you can see, for example, like for given spherical harmonic configurations, we have projected version of how these wavelets look. And as you can see, they were designed from molecular chemistry. That's why they have this orbital type of image when projected. Now, more importantly, back to the physics, enough into the technical details. As I said, I'm someone that has been thinking about these topics of how to extract information in the context of 3D class. So together with Cora working, when I was at Harvard, we set to investigate the extent to which this approach can be harnessed in the context of 3D cosmology. So what we did is that we took some simulations that people have run, thousands of simulations that allow us to perform forecasts. So there are simulations that have been run for a given fiducial cosmology configuration and then for linearized variation steps, so that we can construct numerical derivatives of our estimator and use them to, let's see if I show it here, to evaluate the Fisher matrix, which is the formalism that allows us to forecast how strong, how tight our errors can be. The simulations we used are called these Quixote simulations developed by Paco Villascusa Navarro et al. At the Flatiron Institute. And so we took them, there's like 22,000 of these. We extracted the standard magnet power spectrum, and we extracted this wavelet scattering transform for using 5 different scales and 5 different orientations in this particular harmonic basis I talked about, which generates 76 of these coefficients. And then we also compared against this marked power spectrum, which is another one of these high order statistics. And the reason we compared against this as well is that it had already been applied in these simulations and worked very well. So it was kind of like a part of the competition. Yes.
Well, you are using a Fisher forecasting approach with the magnet transform, but is the scattering coefficient quotient distributed?
Great question. So when we used it for the first time, we took an educated guess based on the central limit theorem that it would be. Actually, it turns out it is. I have got a few slides where I compare the predictions per Gaussian and the actual distribution, and you will see that as long as your spatial veining is wide enough, that the central limit theorem kicks in, it is also Gaussian. But yes, that is a very good point. Otherwise, you can get very optimistic constraints. So this is how it, and the mark correlation function, I don't want to spend too much time on this, but essentially it is a statistic where we take a weighted 2-point function where its galaxy is weighted in an inverse manner by the density. The density is the denominator. The reason we do this is that we know that in most voids are very sensitive probes of fundamental physics. So if we apply such a nonlinear transformation, it turns out, we can break degeneracies and test fundamental physics. Actually, in 2016, Marvin White proposed that we can use this to test gravity, aside from all machine learning stuff or the higher statistics. And actually, this is something I worked on back in 2018 when I was a PhD student. So another slight variation of this is that I said that the modulus is always raised to the power of unity, but we can slightly relax this assumption and allow this index to vary a bit. And the reason this can be interesting for us is that, again, as I said previously, if this is smaller than unity, we can also effectively emphasize on the lower value of this input field, which would be the overdensity in our case, which essentially would allow us to emphasize the cosmic void, which essentially, as we will see, can improve our constraints. But in any case, this can also be applied in the base configuration. And without further ado, this is just a summary of some of the results, where you see here have the 1 and 2 sigma contours obtained on representing the errors forecasted on some of the cosmological parameters, which is sigma 8, the linearized amplitude of fluctuations, NS, the primordial tilt of the power spectrum, and neutrino mass. as given by the power spectrum in red, by this WST in blue, and by this marked correlation in green. And what we find is that, as you can see even visually, the WST, these coefficients, was found to be able to significantly improve, tighten the errors we could obtain in these parameters by a factor of 20% all the way to 4 times tighter, in particular for the neutrino mass. And also the mark, notice the green control, which is this marked correlation function, also did well, but it did even better, especially compared these two. Actually, so this was the first result we got, and it was very important. And even though I will talk about the data mostly, if I jump forward, actually recently, these simulations also now have an expansion that includes modified gravity. And so the same people, Paco Villasuzana in collaboration with Marco Baldi in Italy, also now run an additional allocation of 3 million CPU hours to include a variant that essentially incorporates deviations from general relativity, and we call the FO bar influences model. This is not published yet. I'm writing a paper, hopefully in the next couple of weeks, where here you see that if I add, so this is like a previous result, and here I've added another column that incorporates deviation from gravity, and you see that it seems to be particularly good at improving our constraints when it comes to testing gravity, which makes sense for her. Yes.
Parameters I can see there too small.
Yes, you mean, yes, unfortunately, so it's omega matter, omega baryon, sigma 8, and this H, Hubble constant, neutrino mass, and the Y is the, yes, thanks for this. I should, I was in between, yeah, yes.
What about the bias?
Oh, so here, great question. The bias is very important. This, just because it was a first exploration, it's just dark matter. But from now on, I'm about to switch to using galaxy applications so where we can go about this. But the plan is especially for modified gravity because it's a new thing to then work with the halos and the galaxies.
So this for the simulations don't have galaxies, just dark matter.
So they have dark matter and halos, and for the Lambda-CDM part, they also painted galaxies in the halos, use the galaxy halo connection. But if they're low resolution, so their halos are not, the best colors we have, admittedly. It's just a matter of they wanted to run many of them, thousands of them, but But yes, these are all great questions, which allow me to actually get to, let's say, the real stuff. Because okay, this was all great, but this was like very this was an idealistic setting. Essentially, we applied it to the dark matter field, assuming we know the bias, which is not the case. Real surveys, real 3D galaxy surveys observe galaxies. That's what they call galaxy surveys, which are first of all biased tracers of the underlying matter field. They don't follow this distribution perfectly. And also, in the case of a spectroscopic survey, such as DESI or part of Euclid, are observing rest space, introducing a known anisotropy in the clustering pattern, the way we observe it, which is the rest space distortions. As a result, that means that if we are to use this estimator in the actual world, which is what we've been talking about, we need to do much better than that. Of course, on top of that, we have to deal about particular layers of systematics that have to do with how a survey observes the sky, which is also an ongoing discussion, as I will show. So what we did is that we set to apply it to galaxy data. Before this, let's say the precursory best publicly available data set of a spectroscopic survey is BOSS, part of SDSS, the Baryon Oscillation Spectroscopic Survey, which consists of hundreds of thousands of galaxies that were observed, as you can see here, on both the northern and the southern part of the sky. And SDSS ran for 20 years. And we, in particular, we took the observations in this particular RESI range, in this bin, and which is again a few hundreds of thousands, 500,000 galaxies. Now, for survey data, the input field that we would work with, or plug it into our estimator, is again an overdensity field, but usually traditionally it's slightly different. Usually, we apply a set of systematic weights to our galaxies, which are meant to capture, to absorb these different systematics, called systematic weights. And also, very importantly, usually the way we observe the sky is not a periodic box, it's a mass field. It has a non-trivial survey geometry, which has to do with the instrument. And these are all things that need to be taken into account in our model. And this is what we did. So this quantity, this field here, which is again a weighted galaxy over density field, traditionally it's called the Feldman-Kaiser-Peacock or FKP field. Spectroscopy named after the people that first wrote this paper. And this is a fundamental quantity of interest, which we usually traditionally Fourier transform to get the multiples of the galaxy or spectrum, or in our case, you can feed it as an input into this scattering network in an appropriate form. And this is what we did. And again, talking about the likelihood, which is a great question. When we do parameter inference in particular, not just forecast, if we assume that we have a Gaussian likelihood, this is usually something we work with, where we need to have a prediction or a prediction of our estimator X from the data. We need to combine with a theory model that captures how our estimators vary as a function of the parameters of interest, and also we need the covariance. For the data, as I said, we can extract. We have the data we can extract, assuming we handle things properly. And we did so again using this WST configuration I showed previously. This is, let's say, more straightforward. For the theory model, this is where things get a bit more challenging for any simulation-based statistic, as many of you might have heard, because of the fact that we're talking about a nonlinear estimator. So we can't accurately model how this will depend on the cosmological parameters of interest using just an analytical approach. You can try to do this, but it will not be accurate. So this is where, of course, simulations can come to their rescue. So for this now, we use a better set of simulations, more realistic, the so-called Abacus Summit simulations, which were developed by Daniel Eisenstein's group at the Center for Astrophysics. These are state-of-the-art. These were meant to be used for the analysis of the next generation of surveys, DESI, and beyond. And again, they span variation for most of the parameters, as I will show you here. So you see, it has a grid that spans variations on 8 cosmological parameters. 4, as you can see in this table here, 4 of lambda CDM, again, omega baryon, cold dark matter, sigma 8, NS. 4 extensions to lambda CDM, but simple extensions. One of these is dynamical dark energy, which is getting back into it these days, I'm showing in the end. And then we take this dark matter halos and put galaxies using the galaxy halo connection or models, the halo occupation distribution, HOD, say, which in turn depends on some parameters. These are the known parameters, the HOD parameters, which we use to marginalize them. They are nuisance parameters. So bottom line, without sharing too many details, the dark matter simulations, it's about 85 or 90 of them. And for each one of them, we generate many different galaxy catalogs. So overall, after we do this an appropriate amount of times, we end up generating about 150,000 galaxy mocks, which are the simulations we can use to train this, to learn this dependence, which span variations in the 15-dimensional parameter space, 8 for the cosmological parameters, 7 for this additional galaxy model parameters. So to do this, we extract our summary statistics of interest, like these coefficients, and then we use just schematically a neural net, as we can use these days to learn, to make an end, to make a flexible model that can learn the cosmological dependence of my summary statistic. And this is what we did. Sandy was the expert collaborator in this part. And then I said we need a covariance. For the covariance, there's a second set of simulations, actually, which the Boss collaboration made themselves exactly to enable the evaluation of covariances. It's like 2,000 of these simulations, and we can use them to evaluate the covariance of, you see the WC coefficients to the left. So, and back to the great question you posed, here you can see the black line is the theoretical distribution of chi-square of these covariance mocks if this is a Gaussian. And the blue is the data, the actual data, a histogram of them. And then the orange is the actual Gaussian prediction. And you see that it's pretty much. So this time we tested. And you can see here the same for the correlation function. So you see how both of them are, are Gaussian in a sufficient degree. So after doing all of this, then we have a model. We have a full model to use this estimator to perform parameter inference. But of course, another thing we need to do is, of course, to make sure that the model is accurate enough within our parameter space. So to do this, as is common nowadays in any type of emulation or parameter inference technique or machine learning application, we take a part of the train of the original set of simulations and we put it aside. It does not participate on the training. It's a holdout part, as we say. We train on the rest, and then we try to see if we can pass these test cosmologies through our model, and if we can accurately recover the true known values. So in this case, you see that we know the actual parameters and we pass it through our model. And ideally, we want to be able to accurately infer this within 1 sigma, which we did. Here, I just show a couple of highlights. We did this for a lot of representative cases in the parameter space. And after we convinced ourselves that we did this, we passed all these recovery tests, we could better trust our model in terms of its accuracy, because we want something that is precise. These are slight errors, but of course they need to be accurate. And we do the same also, as I implied, for the standard approach. This time we use the 2-point function, the real space equivalent, the 2-point correlation function of galaxies. And as an additional layer of test, because now so far we've tested with regards to one type of simulations, but a big question in this field, which is likely unanswered, is always, or a concern, is whether I have one set of simulations, but what if they're not accurate enough? And then when I apply it to another set of simulations or an actual data set, I might be thrown off. So here we took a third set, which is actually this universe machine Ucho type mobs that I've been told by experts have a greater dose of realism in how they paint the physics of that information for a known cosmology. We subjected it to our model, and as you can see again here, we are able to accurately recover the true known values for both the correlation function, the red contours, the WST, the blue contours, and their adjoint in black. And now this is an MCMC. This is not a forecast. This is an actual, chain. Yes.
Here, it's probably long theory, whether you want the Fisher like this. Fisher, with the diffusion format, then you are much better results is happening from the pairs of the second. So
yes,
I think we should not be case here.
Yes. That's a very good question. Yes, indeed, the net improvement is not as impressive, at least for all parameters. So there's two explanations which I think it makes sense. One is that when we build an emulator, actually, I made it sound like the emulation error was 0, but it wasn't, just because we have a limited training set. So what we did is that we evaluated the residual error in our emulation and added it to the covariance value. And it seems that for the WST, for whatever reason, it was harder to emulate, so we inflated the covariance more. But aside from this, just to be more conservative, it's also the marginalization over many galaxy parameters. So it's not uncommon, at least as far as I know, to get, when you get an X level of improvement at the dark matter level, when you marginalize over something more realistic, to potentially, see some of this improvement, kind of neutered in a more realistic setting. But still, it's improved. And actually, let me get now to the important part, the data. So this is now, after we do all of this, we pass the test, we apply to the data. So you see again here, first of all, because the previous was also a recovery test. Here we see the data again, WST in blue, 2-point function in red, and the joint combination. First of all, we see the WST alone improves the errors by on omega C, omega colored matter, and NS by actually for omega C still by a factor of 4 just alone. Yes.
It's again very surprising. You can see that the similar statistic and the scattering transform is not providing the same results.
Yes, they seem to have some. I guess this is up to the.
Yeah, but so
they don't capture.
One of them may be wrong, maybe the true, I don't know.
We feel like 1 sigma. So yes, it is true. What you're saying is that they don't have identically overlapping contours, but they don't capture the exact same information, even at the lowest level. They're not the same impressions. I mean, even the first.
Even the same information, right? So you should get the same.
Yes, but they are. I mean, they are not discrepant. They are within 1 sigma. Even if, by the way, we did a great point. I agree. Even if you do this with some more, you train a model for a bar spectrum in the bispectrum, and you do this, you will not get identical stuff. Of course, you don't want your constraints to be in 4 sigma to use your contours, but here they were always, within 2 sigma, even better. So we convince ourselves, but this is a subtle, I agree that, the remaining differences between these two contours are due to the statistical fluctuation, which can happen essentially because they are not identical. The important part which comes from this, assuming of course we have convinced ourselves that this is consistent and genuine, then when you combine this, you can break because they have a different degeneracies. So you can combine and get something even tighter. So in this case, even though we found that after marginalizing or also after adding this error, we get a smaller net improvement. When we combine, we find that the joint combination of the 2-point function and this WSC give us something even better, give us again similar levels of improvement for all the parameters, which allows to obtain competitive constraints on all of these in sub-percent of some things. We can also notice also that these abacus simulations, they have a different gradient as depends on the simulations. It's not the same exact parameters as before, but it is parameters that we care about.
If you run your map to your stations that you had used before, did you try it?
No, but at this point, I'm convinced that it's just the matter. You will always get something much better. It's like what seems to be happening, which I find interesting, but also I guess makes sense, is that the more parameters you add, you introduce more degeneracies that a less constraining statistic like our spectrum struggles and stays behind, meaning cannot break, while a higher statistic will break. So by adding more, you get this interesting net improvement. We're doing more tests now, by the way, for DESI, but they're still not concluded. Yes, another question.
Whose result depends on the number of scales and orientations that you use for the
Yes, it does. So here for this, we didn't play around too much because it's just more expensive because it's an MCMC. But yes, now that I'm going back to do some forecasts and revisiting these configurations, I've been finding that the biggest determining factor, as you would expect, is the scales, in particular the minimum scale, because the smaller the scale you capture, the more information you get. It also it also changes as you remove angular scales. But for this types of wavelets, yes, this seems to be the case. And now we're building more informed basis that allows us to test it even better. Thank you. So this is the result of our latest paper, which has recently just been published, accepted for publication in Physical Review, and which I'm very excited about because it allows us to confirm essentially that we can use such an estimator to actually, get meaningful or more competitive constraints using actual real data. Let me also, and here, when we work with progressive space distortions, a useful quantity that people usually quote is the ratio of F sigma A, the linear growth rate of how perturbations grow times sigma A. This is because the power, this is sensitive to progressive space distortions. And you can see here, we have the Planck prediction, the prediction for Planck 2018 cosmic microwave background experiment. And we have then alongside a lot of other points for past analysis of BOSS, most of them using the 2-point function. Some of them using something like a bicycle. So our result here is in blue, where you see that we are not only getting something that is consistent with the Planck prediction, but we're also getting something that is very competitive. And arguably the most competitive one out of all these measurements, which illustrates the power of using such a new estimator in principle. And even though it is not a lengthy thing, but we also will evaluate SA as a derived parameter from the chain, which is consistent with Planck. But SA perhaps is not as important for galaxy clustering. Here you see, by the way, the summary statistic. We have all the errors tabulated. Another thing, usually, it's fun how things change. Usually, this is where it's in the end of the presentation. Usually, at the end, I have the equivalent constraints we get when we include extension to the system. Because remember, I said that we have an 8-parameter grid that includes extensions, but then I focus my simple number CM on the standard cosmological scenario because, of course, this is the standard one. But if we allow these extensions and try to constrain them, we find that we can using the joint combination. Of course, the constraints now get relatively wider because now we introduce more parameters. You can see here, this is W not the WA. These are parameters capturing dynamical dark energy. We didn't find for boss using this any signs of deviation from CDM, or to put it differently, the one sigma constraints of the parameters capturing the deviation from CDM, that is, these are consistent with the lambda CDM limit within within 1 sigma. And so again, I'm very excited about these results because they open up essentially the opportunity to now apply these types of techniques to fully harness the power of the next generation. So this is, you might have seen, the dynamic spectroscopy instrument that I am a part of is already ongoing. They recently released, as I will show briefly, their first-year analysis using the baryon acoustic oscillations. And as part of this, there's a very active effort to apply a variety of types of such alternative summary statistics. And as part of this, I'm leading the effort to apply this wavelet scattering transform to the first year of DESI data. And as a result of this, we're trying to make a uniform pipeline subjected to a layer or layers of more thorough tests before we convince ourselves we can trust it. And in particular, now I guess I should be particularly excited because, as I said, now results are out. You see here, I like this visualization made by Claire Laman, a student at Harvard, where you see this is actual data. Of course, they use the visualization tool, but these are actual galaxies that DESI observed, the bright galaxy sample, where you see that we can clearly see the nice filamentary structure of the cosmic web. And perhaps more importantly, this is what a lot of people think about. This flow has generated a lot of controversy, and we can talk about this, asking about it if you want. Because essentially they found that when we allow ourselves to explore a more general scenario about dark energy with the time varying equation of state, there's some weak to moderate evidence up to 3.9 sigma of a preference away from the standard scenario, away from the. This is still preliminary in terms of what it means about our universe, but very intriguing, tantalizing hints of something different, they called it in the abstract. And it's very controversial, depends on who you ask. There's a lot of talk these days. So for me, it just gets me very excited because essentially it promises, it sets the scientific scene about using all these types of estimators alongside the standard approaches to learn hopefully something about the composition and the history of our universe. And having said that, let me summarize here. Let's see. Okay, right on time. So I talked about the wavelet scattering transform, which is a novel summary statistic that promises to essentially extract non-Gaussian information out of a physical field and serve as kind of a more ideal middle ground between traditional estimators and simulations. And I showed through a series of 3 papers that has culminated with our 3rd paper that has now just been published to the physical review team, that we can actually apply to real data for the first time. Now, recently, there was also an application also to weak lens, but this was a very, very first application of data ever. And for that, I'm very excited about. And of course, I'm excited, but there's always better, you can always do better. So as a result, we're working actively within and outside DESI to improve the accuracy of our model using more accurate simulations and better tests and simulation-based strategies, and also, of course, to make better wavelets, because these wavelets, as I showed, they were designed for molecular chemistry, but for a particular application to cosmology or to whatever your favorite physical system is, one can imagine that we can make something more suitable, and actually this is the case. So I have some other collaborators, also the Flatiron Institute, that have been working also on wavelet transform. So together we are working with a better, more suitable basis, in particular an anisotropic one, because when we work with RSD, we have an anisotropic. And we will hopefully have a public package that we will make available together with some new exciting physical applications. And having said that, in terms of the physics one can do, of course, yes.
So you are developing an anisotropic wavelet transform?
Yes.
With scattering transform, you have several iterations, so it's not that.
That is a great question. So it seems that actually, when I first worked on this, I said yes. I was like, or I was more convinced that because it has different directions in these solid harmonics, you can capture all of the anisotropic. But then a lot of mathematicians got a bit not mad. It's just we had some discussion because apparently, even though it has directions, Apparently, even though it has, an angular dependence, even the sort of harmonic case was designed to be isotropic. So apparently, this estimator that we use, even though, it can do well enough, it doesn't capture, naturally all the angular information that they have out of that. The way to do this is that if you have a preferred direction, like, which in an RST survey would be the direction of the line of sight, you can define something around it in symmetrical coordinates and, have a more natural way of capturing everything about them. So this is what we're doing now. Actually, we will see, they also have results that came out after ours, but our models have a lot of pieces that are different. It's very hard to compare how the two are doing unless we do them on an apples versus apples basis, which we also plan to do now. And in terms of physics, as I said, now we're about to apply to DESI. And also people can apply to Euclid, as I said. People in Euclid, I think, are already thinking about this at the point of lensing, but spectroscopy is also an interesting thing. And as I said, there was an HSC lensing application very recent. You can see how would be a Cosmo 21, we'll probably talk about it. And in terms of the properties of physics, I talked about either lambda CDM, minimal topological scenarios, or constraints to simple extensions. But one can do a variety of things. As I said, there's a modified gravity application in the works. Just with dark matter, one can actually, some people from Italy recently put out a paper using this approach to test primordial non-Gaussianity. So you can think about parity violation, axioms, there's a lot of things. Whatever is sensitive to non-Gaussian information, you can in principle test. And of course, have the data sets. Actually, there are, to conclude, proof of concept papers that have been written after we worked on this, trying to explore this technique in the context of other cosmology probes, such as the Lyman alpha forest, 21 centimeter cosmology, and even some action-induced string effects in the CMB, but more of them, say, proof of concept. And of course, the future is bright in between DESI and LSST and Euclid. People in the DES survey are also about to put a paper out applying this to their data. So having said all of this, I'm very excited about this new field, emerging field. Hopefully, I did a good enough job of sharing some of my excitement with you. And having said all of that, let me conclude here, right on time, and see if there are any further questions. Thank you very much. Yes.
So you find in your constraints at the end that adding the keyboard statistics to the WST still improves significantly the results, right?
Yes.
Which is a bit surprising because with lensings, with some other wavelet-based statistics, they have found that they essentially capture the information that is inside the Gaussian statistics as well.
So yeah, I think a reason that it's different here, aside from the fact that it's a different role, there is one subtlety in our particular wavelet basis. So as you might know, in 3D clustering, your larger scales are also informative because you have the barrier oscillations. So which is actually what DESI just used for their. So our wavelets, because it does the way they were designed, they didn't fully capture the BAO. It's mostly small scales. So essentially, the 2-point function captured the BAO, the WST captures smaller scales, which give you a lot of constraining power, but are lacking something. And then, when we combine both, essentially we can combine WST with the BAO. A better wavelet basis shouldn't need it. It's just we haven't used it yet. Yeah.
But the fact that they both, as you show, give the same answer as you were arguing within 2 sigma,
Yes.
doesn't that mean that in the end there is no extra information?
I mean, let's put it this way. Let's say that we have a summer statistic that starts from large scales and goes all the way to small scales. If you cut out the larger scales, the result you get might be consistent, might be a contour that is consistent within 1 or 2 sigma, but it might be wide. So this is meaning there's 2 things here: whether they give something that's consistent within 1 sigma, and whether the increasing sigmas either of them gives is better. Right? So meaning I say that they're not compatible in that they agree in what they give within 1 sigma. So in terms of accuracy, but they give some difference in terms of increasing size. But both are in play, actually. It's just when you have a different compression, it's a bit harder. Because also this, even at first order, is not exactly power spectrum. As power spectrum like, it's a different wavelength and it's a different essentially module based thing. So, but yes, these are all interconnected aspects. Yes?
You showed that there's also random and that maps with a similar.
You mean the Quixote, the simulations?
No, I mean, you said you showed the Valogiannis.
Ah, yes.
So, does it able to, for the non-Gaussian maps, this method will identify some features, right?
Yeah.
This method will have more details in an analytical context.
This is quick lesson, keep in mind. Yeah, no matter galaxy field will have in principle, but I mean depends also on the choice. But actually, I mean, that's why I need to make this plot for our case. Yeah, if you overplot a Gaussian field with a fully non-Gaussian field together, depends on the scale. Yes, you will see difference, especially in the if you plot halos or galaxies, you will see different mergers and stuff like that. But which can in principle be exposed with a suitable basis, and which I should make, by the way, to better motivate this. But yes, absolutely. Yes.
I want to ask practically how expensive is WST?
Good question.
Compared maybe to point or to a simple CNN?
Yeah, good point. Good point. So, like with this already for Mario package is GPU accelerated. So the GPU for this configuration, it's about just a few seconds at the GPU, so it's fine. But yes, it's true that I say that it's simpler and it is more expensive. It's cheaper than a CNN, but if you don't have a GPU, it's a bit more expensive. But with a GPU, it's much cheaper than the CNN because essentially, you don't need to repeat this procedure to get the parameters. But yes, I forgot to say actually. So thanks for asking this. Yes.
So in practice in the past, light spectrum has been the favorite tools for hydrostatistics.
Yes.
And light spectrum has the advantage that you can derive some theory. So
Yes.
you don't have to go through simulation, you can directly compare to theory.
Yeah.
So here you have to go to simulation and you have to have the addition to having the simulation, you need to have a neural network to interpret the parameters. So it makes everything complicated and less reusable. So the first thing I will ask you is being compared to light spectrum. You are improving over standard hydrostatic tools.
Good question. Yes. And we have to admit that however, how the expression says that everything has a cost. So the cost of this is that in any type of type of estimator, you kind of abandon the power of the analytical perturbative approach. So two things. I have not compared here with the bispectrum just because of limited resources being used as me. Some of the people I collaborate with, the Flatiron, they have these other simulations which are smaller in terms of volume, but they also analyze the part of the sky and the different people within that, because all of them did bispectrum and WST. So there are some comparisons, and I think it does better, but I don't remember if they explicitly quoted the number. So I don't have a number in my mind, but I think it does better. And to the second thing, even though this is, if I go to the very end, even though this is kind of an esoteric argument, but this is very interesting work, which, sort of, very end. Okay, this is very interesting argument. Cheng and Menard, they showed it in their paper, and it's also related to some work that Julian Caron has done in the past, which shows that this is the feature information in an instance where you have an analytical prediction for the feature information. And here it shows, how much of it you can get just in different moments. So and this axis shows you, the degree of non-Gaussianity of your field. And it's a toy model, so you can, predict all this analytics. So essentially, there's an argument to be made that if you go to a high degree of non-Gaussian configuration, in here, even if you know all the moments, not just the 3-point function, but all of them, your ability to capture the available information is diminished. Actually, at an extreme, it might go to 0 just because you have a very complicated probability distribution that your endpoint functions cannot capture. Here, in this work, they try to see what happens if you make a similar prediction for this toy model using the scattering transform up to second orders. So, or they found that this is you can get more because it's a better, let's say, compression at capturing non-Gaussian. Of course, this is an argument from, let's say, principle. This is not the galaxy distribution, but it motivates, let's say, going beyond.
And how does it motivate compared to the bicep?
In that, Cindy said that if you're here, if you use not just the bispectrum, more higher order correlation functions, you get essentially a very small fraction of the available distributions, whereas the scattering response can get much better. But of course, this is an argument, a theory argument, not hasn't been applied in that fashion. And I agree that actually the multi-graphing thing now, because there's more of us collaborating, someone else is doing bispectrum, I'm doing the WC, so now hoping we will also be able to have it. And also there they forgot, because now it's a collaboration, there's again different people doing different summary statistics, including the bispectrum. So hopefully we will have the ideal thing, which is an apples side-by-side comparison, how they do for the same scales and all that. But in principle, yes, I believe it can do better, especially if you optimize it because of these like theoretical arguments. But yes, good point.
This is very confusing to me. What do you mean all moments? Because there are infinite moments. Right?
Yeah.
And, and they contain exactly the same information. If you take them to infinity, they support exactly into the real thing.
So apparently the argument, and actually, yeah, it is an argument that it's a PRL from 2012. The argument is that if you have a very non-Gaussian case, but if you work with a toy model where essentially there's an analytical expression of the Fisher matrix as a function of all the moments, even if you take it to infinity, you can't get everything back. This is something I wasn't aware of, but apparently there's an argument from in principle, and this has to do with the fact that in a very non-Gaussian configuration, you have a heavy tail of the probability distribution, and apparently even with infinite moments, you can capture this. That's the. Of course, how close this is to the galaxy field depends. So maybe this is an extreme case, but I know, right? Meaning what this means is that in principle, all moments don't guarantee giving you everything back. Yeah, and that is true. That is something I didn't know until I got into this.
But it means that that description is incomplete.
Yes, yeah, exactly. Meaning, even though we're not sure about the degree in which we are at in cosmology, it seems that we should challenge the notion that the endpoint function hierarchy gives you everything. Seems that it doesn't necessarily, maybe. And while for the full field level information, maybe you need something more or machine learning. But yes, it is like something that there are theoretical arguments and arguments from in practice, and it depends. And as it's a new emerging field, people are catching on to this, but it's still, that's why it's still an open question. As convenient as it makes sense. Thank you.